Now you know that this is r square dr sine theta d theta, right? Sine theta d theta. Sine theta d theta. Can I write it like d of cos theta?
Yes, sir.
Because the differential of this will be sine theta.
Minus sine.
Right? Minus sine theta. And d theta. Because d theta will be further differentiated. So minus is coming in there. So keep in mind that minus sign. Now, how this d theta is varying? It is varying from 0 to pi. Sin theta is d theta is varying from 0 to pi in this one when we are writing this element. So what about cos if I now vary d of cos theta? So in cos 0 this is equal to plus 1 and cos pi this is equal to minus 1. So if I write from plus 1 to minus 1, then I will write d of cos theta. But as you know, one minus sign was coming in there. So I will adjust that minus sign here. Then I will start from minus 1 to plus 1. This way. So this is an easy way to write this thing from minus 1 to plus 1 and d of cos theta. So this one, the differential will directly cancel with the integration, and I will only put the value of plus 1 and minus 1 here. Similarly, this will give me 2 pi. This will give 2, and this will give 2 pi. So I will have that this thing is equal to principally this thing is 4 pi, means this is the solid angle. 4 pi. And this one is r square, right? This one is r square. But the result should come out to be 1. It means in order to balance the dimensions of this, I should have my delta function like this, that delta of x is equal to 8 times delta r and 1 over r squared. Now look, 1 over r squared will actually manage this r squared. And this constant will manage this solid angle. So then it will be normalized or dimensionally correct. Otherwise, our delta function conversion will not be right. Now, from here, I know that A is actually equal to 1 over 4 pi. A inverse is equal to 4 pi. So A is equal to 1 over 4 pi. So I can write that delta x is equal to 1 over 4 pi r squared delta r. Clear? Is it clear? Okay. Just I'm repeating this one. This one was equal to 1. Now this side, in order to make it equal to 1, this is delta x. So what I will do, I will write that the delta r that I will introduce, because I will say that this one is the relevant delta, because it is having the dimensions of length in it. The dimensions of length here are here, while this one is the angular dimension. So the angular dimension means they have nothing to do with the linear length. So you will have to just normalize it by this equation, 1 over 4 pi r squared. And whenever I think you have proved this one, when there is a problem with the divergence pair, then 1 over r square divergence you have corrected with the delta of r. Similarly, this is in spherical polar coordinates. Spherical polar coordinates. And if I select spherical polar coordinates, then delta x will be equal to 1 over, and this will be 2 pi r. 2 pi will be the angular portion, and 1 over r will be just to manage the r dr, and then delta of r. And similarly, this will have delta of z as well, because there are 2 dimensions. So with the help of this, we can say that we can write our delta function. Now, by the way, what's the dimensions of a delta function? The dimensions of a delta function are always the reciprocal of its domain, right? The reciprocal of its domain. Like you have written delta x, right? So delta x here, you are multiplying with volume. So this delta x should have the dimensions of 1 over volume. Otherwise, dimensionally, this equation is not correct. If you write here like this one, dx delta x and f of x. So here is f of x. So the dimensions of this side are equal to the dimensions of this one. Then it means this portion should be dimensionless. And when it will be dimensionless? When the dimensions of this one will be 1 over x, then dimensionally it will cancel. So in one dimension, if I write dx delta x, then this delta x will have 1 over x dimension. If I write this in 3 dimension, d cube delta x, then this delta x should have 1 over x cube dimensions. Otherwise, it will be dimensionally wrong. So the dimensions of delta function of this delta are always the dimensions, the reciprocal dimensions of its domain. So I know that if it is only delta x, if it is only delta x, then it will have the dimensions of 1 over x. And if it is delta, and how I should differentiate, let's say if this one is the x variable, and then I say that this is now xi, like x1, x2, x3 means x, y, z. Or I write this like this x, y, z, then it will be 1 over x cube dimension, 1 over volume dimension. Now I can write this thing, which is rho, and rho is actually equal to d cube times x into rho. So I can write that if I multiply q here with 1 over delta v, then I will have charge density. So if I multiply this q with delta function, right? If I multiply q with a delta function, then if the delta function is in 3 dimensions, then it means its dimensions will be 1 over volume. So for 1 over volume, I can write the delta function. So I will redefine my charge density is rho of x is equal to summation on I, qi, and delta x minus xi. Clear? Okay. This is charge density. Charge density is charge per unit volume. This is the total charge. Now what is this one? It is not one dimension. This is actually three dimension. Why? Because it will be x minus x1, x minus x2, x minus x3. So these are three dimensions. Each of them will be 1 over x, 1 over x, 1 over x, so 1 over x cube. 1 over x cube is actually 1 over volume. So charge per unit volume you define is charge density. Clear? So this is the new way to write the charge density. Writing charge density in terms of delta function. Because it is this delta function which will pick one charge, one point charge from this continuous distribution of charges. Clear? Or from the cluster of charges, you can pick one charge. It's a point charge, so point function is required for it. So now we start with the. It is very difficult to find the interaction of charges or the field of charges when they are more than 2, 3 or 4. So we need the Gauss's law in order to calculate that for us, because we will apply superposition principle, and from the superposition principle, if there will be 4 charges, so 1 with 2, then 1 with 3, 1 with 4, and then 2 with 3 and 4 and 1, and means it will increase. So in order to avoid that superposition principle, we enclose the collection of charges in a given surface according to the geometry, and then we apply Gauss's law on it and calculate the electric field. So if I'm having a charged particle, let's say this is a charged particle Q, and this charged particle is enclosed in this shape. So I'm having the electric field in this direction, and this page element which I am considering here, let's say it's in this direction, which I will call n unit vector. So this E, the electric field line, will have an angle theta with it. And for this I can write the electric field is equal to K Q R over R cube. K Q R over R cube. Now instead of writing it in x minus x1, x2, I am just writing it in R. If I multiply with this, the area unit vector n dot E, then this will be K Q n dot R by R cube. And this one I can write is K Q and R cos of the angle between the two, and divide by R cube. So you know that n dot E will be equal to K Q. R will cancel, so I am having cos theta divided by R squared. Right? Now if I am multiplying dA on both sides, then n dA dot E is equal to K Q and cos theta dA divided by R squared. And I know that this one, okay, if I I write it in unit vector dA, then it will be, this dA will be scalar. But I can write it as E dot dA. So then I will write area as a vector, and this will be NdA will be dA, and this is equal to KQ. What about this one? Cos theta dA r square. This is actually the solid angle. This is 4 pi. If you look at it clearly. What was the area element? Area element is r square sine theta d theta d phi. If I do the sine theta d theta in it and d phi in it, so what it will be? 2 pi from there and 2 from here. So it will be r square times 4 pi. So 4 pi r square. 4 pi r square is what? Solid angle. 4 pi is solid angle, not r square. But r square is cancelling here. So it means that this value is actually the solid angle, d omega, which is 4 pi. So I can write d omega here, and if I do integrate on a closed surface, then E dot dA is equal to K, and then integral Q d omega. And I know that this is K and 4 pi Q. Because d omega will integrate to omega, omega is equal to 4 pi. So this is equal to this when Q is enclosed, and this is equal to 0 when Q is not enclosed. Means our Gaussian surface, if it is not enclosing this, then this thing will be equal to 0. Similarly, I can write this thing is 4 pi, this E dot dA, I can write like this, 4 pi K, and summation on I and all charges Qi. All the charges which are enclosed. So this I can write is, this is equal to 4 pi K, and then this, I know the value. What was the value of Qi? It was rho of x d cube x, means the enclosed volume. I can easily convert this one into differential form, which we have already done this thing. Okay, now here 4 pi and here is k. K is 1 over 4 pi epsilon naught. So 4 pi will cancel with 4 pi, and this one is q. So q over epsilon naught. We have studied this form, very, you can say, easy form, that E dot dA is the q enclosed over epsilon naught. This we have studied the simplified form, but we will, you can say, go on with this one. That this is the same as this one. Now, you can very easily convert this thing into differential form by applying the divergence theorem, and then we have already done in the review. So I can write that in differential form, this one can be written is divergence of E is equal to K 4 pi and rho. So it will be rho over epsilon naught. 4 pi with 1 over 4 pi cancel. So it will be K 4 pi rho or 4 pi K rho as you like. If you put a dot here, so if we are writing this thing in CGS, then it means K will be equal to 1. So it will be 4 pi rho. So this way you can do very easily to just make K equal to 1. Introduction of scalar potential. Introduction of scalar potential. Now these days it's a very hard debate as well, that if means electric field is 0, V is constant, then electric field is 0, then who is generating this potential are questions like that, equipotential surfaces and all these, because it's a question in FSC book, textbook,